the previous lecture we had talked about the free vibration of various structural members that led to an eigenvalue problem which we solved to find the characteristics of the response of a solution in free vibration, of a system in free vibration. We will now extend our analysis of transient problems to the case of forced response. We could also do the free vibration analysis using a direct time solution, that is, we do not do the separation of variables straight away and separate the spatial and the temporal part, and we solve for those spatial and temporal part together. So let's see how we are going to do it. We will do the temporal or the time analysis. So let's consider some typical differential equations corresponding to physical problems which arise in the case of transient analysis. One case is what we call as parabolic equations. The parabolic equations, a typical example is the heat conduction problem. What we had done long ago was a steady state heat conduction problem. When the heat conduction is not in steady state, that is, heat is actually flowing, there is a transient, then it would lead in a simplified form. Let's say I have again a member. Okay. Here I specify temperature is equal to T naught. I have in one dimension the source term, the heat source term, R as a function of x and t. Okay. And here is my boundary flux term, heat fluxing out. This is given by G, let's say, as a function of T. Then it can be shown that the governing differential equation would be of the following type: some constant into delta T, the change in temperature with respect to time. This is essentially the buildup of the internal heat with time. Okay, this will be equal to the amount which is produced by the source minus the amount which is fluxing out. Okay, so this would give, implies C the del T plus Qx is equal to R. Qx, as we have seen in our basic mechanics courses and the heat transfer courses, is nothing but minus some constant k into the partial of T with respect to x. That is, heat flows from a hotter to a cooler region, so it flows in the direction opposite to the gradient. That's what we mean. Okay, this will be del x of Qx. Okay, so this will be del x, because we are talking of an infinitesimal volume, so this is what you will get. This you can check in any book on mechanics on heat transfer, or you can take an infinitesimal piece, look at the heat transfer in that infinitesimal piece. Okay, flux coming in, flux going out, and so on. Okay, so this equation now we are going to work with. So I have C del T minus del x of k del T del x is equal to R of x. Okay, x and t, R of x and t. I have to remember that here my source can change with time. How do I find a solution to this problem? Okay, and okay, for every point in the along the member and for all times from 0 to time capital T. So here, in order to find the solution, we will follow something which we have been following till now. That is, we are going to talk of the instantaneous weighted residual formulation. Okay, we will talk about it a little later. Okay, first let's look at this solution. If I look at this problem, the solution to this problem in time behaves exponentially. Okay, that the solution will have e to the power of minus lambda t kind of behavior. So it is very smooth in time. Okay. Another type of differential equation that we come across very often is the hyperbolic problem. Okay. An example of a hyperbolic problem, we have been doing this for a long time now. There is this bar subjected to axial forces F, which now can change with time, and an end force P, which can change with time. Okay. Here the u is equal to 0 for all times. Okay. So then for this bar, if I look at the equation of motion for this bar, okay, again taking an infinitesimal piece and looking at it, I will get that del x of EA del u del x, okay, plus F is equal to rho del to u del t squared. So wherever I have a derivative with respect to x, I will write it as a prime. Prime will indicate a derivative with respect to x. Wherever I have a derivative with respect to time, I will also use the dots. So a dot means derivative with respect to time, two dots second derivative with respect to time, and a prime will mean a derivative with respect to x, the spatial derivative. So this is the equation of motion for the bar problem. Okay, this is a hyperbolic problem, and as we had seen that in case we do not have the force, this forcing function f, we do not have it, the free vibration problem, then the solution behaves both in space and time in an oscillatory manner. That is, the solution is oscillatory both in space and in time. Okay, this is a feature that we have to keep in mind. So solution here is oscillatory in time. Okay, and we had discussed that as far as resolution of the solution in space was concerned, that is, in order to get the natural frequencies and the modes properly, our finite element approximation in space had to be sufficiently fine to be able to represent the mode properly. Okay. Similarly, in time, when we do the temporal approximation, our approximation in time should be sufficiently fine to be able to capture the corresponding oscillatory behavior in time. This is something we have to keep in mind when we go ahead and construct temporal approximations. Okay. So let's now go and look at first the parabolic problem. Okay. So if we go back to our parabolic problem, okay, this differential equation, and try to construct a form which can be used in the finite element formulation. So I will take, what will I do? I will take the instantaneous virtual work formulation. Virtual work or weighted residual formulation. So we take the differential equation C minus, let's say K is a constant, and multiply both sides with a weight function W and integrate from 0 to L. Okay. Once I have done this, then again I do what we have been doing so long, is we do integration by parts. So integrate by parts. Integrate which part by parts? It is the spatial derivative has to be seen, okay, and that has to be integrated by parts, because here we are doing the integration over x. So we will have to take care of this part when we do the integration by parts. So how do we take it? So this will give, integration by parts once will give, watch this very carefully, that this is going to be w plus k del t del x del w del x dx is equal to integral 0 to L rw dx plus k del t del x into w evaluated at 0 and L. Again, the same issues arise as far as the choice of w is concerned, admissibility of w. It should be such that the first derivative of w is defined. Similarly, the first derivative of t should also be defined. So I use C0 approximations for both t and w. And you see the boundary condition here, this is term which is given at the two extremities of the member for all times. Remember that this boundary condition has to be expressed for all times. So the way we have drawn our figure, that at x equal to 0 the temperature is maintained, okay, if you see from the figure, is maintained to the value T0 for all time, okay, which means that at that end W has to be chosen to be equal to 0, because temperature at any instant is known at that end. So at x equal to 0 W is 0, so that part gets cancelled out. At the other end, at x equal to L, we have that k del t del x, the flux condition, is given equal to G. So we have exactly the same boundary conditions, that is the flux at the end x equal to L and the temperature at end x equal to 0. So we will say that this quantity is given at the end x equal to L, and we will say that this whole thing will be equivalent to G into W at L. Okay. So look that here in this problem we have boundary conditions coming in just like we have been doing it till now. This will be either temperature is specified or the flux is specified. Okay. So these two quantities either or have to be given at each end, okay, for all times. Now we ask a question that, fine, I have this formulation, then what do we do? Okay, how do we use this to construct a solution? So the basic idea is that I will take the same representation in space for t as we had been doing for the static problem. So t as a function of x for the static problem was sigma. I will put some coefficients, okay, coefficients, it will be ti, okay, phi I x, I is equal to 1 to number of degrees of freedom n, where phi I our usual C0 basis functions, okay. So you could use the hat functions, you could go ahead and use the Lagrangian shape functions that we had talked about over and over again, okay. Now when I want to use this representation to write the solution as a function of space and time, we use variation of parameters approach. That is, these parameters ti, the coefficients, will become functions of time. So in our representation we are going to now use a variation of parameters approach, okay. So these are functions of time. Okay. So this is the approach that we are going to take in a representation, and you see that very nicely this fits into the scheme of things the way we have been following it, okay. So once I have this, let's Let's take a example. Let's take a simple example that I take a mesh with just two linear elements. Okay. So what will the basis functions look like? They'll again look like this. Okay. So here, if I look at, so this is my phi1 as a function of x, phi2 as a function of x, phi3 as a function of x. This is node 1, node 2, node 3. Okay. So my t as a function of x and t is equal to t1 as a function of t, phi1 of x, plus t2 as a function of t, phi2 of x, plus t3 as a function of t, phi3 of x. Now what is the boundary condition? T at the point 0 for all times is equal to t naught of t. Okay. So this will be equal to what? For x equal to 0, phi1 is equal to 1, phi2 is equal to 0, phi3 is equal to 0. So this is going to be equal to t1 of t. Okay. So what we have obtained is that the value of this coefficient is obtained from the given boundary condition for all time. Okay. So then it becomes relatively easy to see what we are trying to do. This and this coefficients t2 and t3 are the unknown coefficients that we are after as far as the function of x. What will happen here? How will I have the w? Instantaneously will be equal to beta 2 phi 2 of x plus beta 3 phi 3 of x. So this is how we are going to choose the representation of the finite element solution. So I will do Fe, this is Fe. Okay. So this we have to keep in mind that this is the finite element solution. Now if I take this representation of the approximation for the temperature T, we put it back in this formulation that we have done. So we will get integral 0 to L, okay, C in terms of the derivatives. I will get I is equal to 1 to 3, okay, del Ti del T phi I. For our particular problem, in the general case, we will replace this by n. So let me replace it with n in the general case. Okay, n fine into w plus k into sigma Ti phi I prime. Prime means derivative of phi I with respect to x. So wherever the time derivative is concerned, I take the derivative of the coefficient. Wherever the spatial derivative is concerned, I take derivative of the basis function. Okay, this into w prime dx, okay, is equal to the right hand side. Okay. So next what do we do? So next what, it's quite easy. Again we choose to construct the required number of equations. How many equations do we need? In the special case that we have taken, we need only two equations because there are two unknowns t2 and t3 as a function of time. In the generic case, we need, if it is for a mesh of say n minus 1 elements, we need only n minus 1 equations because the first equation as the first degree of freedom is known. Okay, so choose, will in a generic way we will choose w is equal to phi I of x. So I will get the ith equation, okay, which looks like integral 0 to L. I will put sigma I is equal to 1 to n C del t, sorry, not I will now put it j, because del t phi j into phi I plus sigma j is equal to 1 to n, okay, k t j phi j prime phi I prime dx is equal to integral 0 to L r phi I dx plus p into phi I at L. So this is essentially our equivalent of the weak form that we had obtained for the static problem here. Just let's look at it. Here the solution is in terms of these unknown coefficients Tj and their time derivative, okay, the first derivative of it. That's why it's the parabolic problem, because the first derivative of the unknown coefficient with respect to time is sitting here. Okay, so if I write it now, this will be equal to writing it as sigma Tj dot j is equal to 1 to n integral 0 to L phi j phi I c dx plus sigma j is equal to 1 to n Tj integral 0 to L c k, not c, phi j prime phi I prime dx. Okay, this is equal to integral 0 to L r phi I dx plus p phi I at L. Okay, so I will call this whole thing, this integral, I will call as the big Cij. This integral I will call, which you have already seen, as the big Kij, and this whole integral is Fi. Then I can write this problem, rewrite it in the following form, that C into T dot, where the vector T dot, which contains these components T1, T2, T3, T4, okay, plus K into the vector T is equal to the vector F. Okay, this is the matrix form of this problem. You see that what has happened is we have now written this in terms of partial or time derivatives of these unknown coefficients and the values of these unknown coefficients. So this becomes an ordinary differential equation for these coefficients Ti in terms of time. Okay, so our job is now to find how these coefficients change with time or evolve with time. Okay, so what do? This ordinary differential equation, this is actually a first order differential equation, now can be solved using finite difference approach. Okay, so as far as taking care of the part, the variation with x, we used what we had been doing till now in the standard finite element form using the basis functions. We integrated the x part out. We got equations in terms of these unknown coefficients Ti and their derivatives. Okay, so this leads to a first order system in terms of these Ti's and their derivatives, which we have to solve. Okay, what is the idea of the finite difference approach here? That I start so start at time t equal to t naught, which is equal to 0, and we do a marching in time, which we will call as time stepping. Okay. That is, we take these increments in time as delta t. These increments could be different for various time stations. Okay, increments in time. Okay, now t I is equal to t I minus 1 plus delta t. Okay, I is equal to 1, 2, okay, till we reach the desired final time t. Okay, it could be the time when the solution reaches steady state. It could be some cutoff interval for obtaining the transients. It could be the long time behavior. Okay, so all sorts of requirements about how far we want to march with respect to time. Okay, and what we are doing is we are trying to construct solutions at each of these what we call the time stations. So we would like to obtain the value of these coefficients at each of these time stations ti. So that is the coefficients at the time station ti is what we want to construct. So given these coefficients at the station ti, we can construct the whole response of the the temperature profile as it changes with respect to time, response over the whole x as it changes with respect to time. So that whole picture we can construct. This approach that we have taken is called a semi-discrete approach. Okay, why is it semi-discrete? Because we integrated with respect to x to convert the equations to these discrete equations, ordinary differential equations in terms of time, in terms of these discrete variables ti. Okay, this looks very much like the motion of a multi-degree of freedom spring mass damper spring mass system. Okay, where each mass we are interested in its motion with respect to time. So these coefficients represent something similar. Okay. Now there are standard ways of doing this time marching. So what we are going to use is the approach, the alpha family of time marching schemes. The basic idea here is that if I am given the coefficients ti for time intervals I minus 1, I minus 2, because if I know it for I minus 1, I know the values of these ti's at all time intervals up to I minus 1. So I know for I minus 2, I minus 3 and so on, and using that I construct the solution at the time interval ti. So given the value of this tj's at time station I minus some small n to tj at time station t I minus 1, I would like to obtain tj at the station ti. Okay. In our standard connotation, we will call it tj at station I minus n. This means that it is at time station I minus n, and this I will call as tj at station I. Okay. So given these, I would like to obtain it. The alpha family uses the value at the previous time station. Okay. So how does it go about doing it is the following. Okay. So here we have that t j I, let us say I know the value at I minus 1, minus t j I minus 1 divided by delta t. Okay, if we are using uniform time steps, if not, we use the variable time step. This is equal to 1 minus alpha into t j dot at station I minus 1, okay, plus alpha t j dot at station I. Okay. So, if I am given the solution at time I minus 1 and its derivative, temporal derivative at time I minus 1, then I can construct the derivative at time I in terms of the unknown value of this coefficient at time I and the values at time I minus 1 and the derivative at I minus 1. Okay. This is the alpha family of temporal approximations. Okay. So, now the question is, if I do this, then we can see that this will imply that t j I minus t j I minus 1 is equal to 1 minus alpha delta t into t j dot at I minus 1 plus alpha delta t t j dot at station I. Okay. So, now what can we do? So, we have, if you remember, our differential equation. If I go back to the differential equation that we have created, you see, if our c is, let us assume that c is not a function of, the small c is not a function of time. Similarly, the k is not a function of time. Okay. In that case, we can say that this matrix Cij, the components of this matrix, are independent of time. The components of the matrix Kij are also independent of time. In case they are, it is not a problem, then these components will also become functions of time and we will evaluate them at each time station. Here, for simplicity, we will keep the C and K independent of time. Okay, so we have here, so given this, then the equations will become C at time station I minus 1, I will get C into t I minus 1 dot plus k into t at the station I is equal to f at the station, t at I minus 1, f at station I minus 1. So, this is at the time station I minus 1, because this equation has to be true at each time station. Similarly, I will also have C at station I, t dot at station I plus k into t at station I, this is equal to f at station I. Okay. These things are known. I mean, these are the equations that we have. Okay. So, now we come here. In this, what do I do? I am going to take this equation and say that here I will operate on this with C, operate on this with C, okay, that is with Cij. So, what will I get? This equation will be equivalent to writing the following, that the vector t at station I minus vector t at station I minus 1, okay, is equal to delta t into 1 minus alpha into the vector t dot at I minus 1 plus alpha t dot at I. Okay. There I wrote it for the component, here we are writing for the whole vector. So what I am going to do is operate on both sides with C. So I will have C, C, here is C, and here also I will have C. Okay. So if I operate on both sides with C, so I will get implies, and then we end up getting C into t at the station I minus C into t at the station I minus 1 is equal to 1 minus alpha delta t, okay, into C operating on t dot at the station I minus 1 plus alpha delta t C operating on t dot at the station I. Remember that t and t dot at I are not known. Okay. So what we have done by doing this, we have expressed this at time station I in terms of C into Ti at the time station I. Okay. So this will give me alpha delta t C into t dot at time station I is equal to, from what we have done, it will be C Ti minus C Ti minus 1. So C at time station I minus C into the value of t at the time station I minus 1, okay, in minus 1 minus alpha delta t into t dot at I minus 1. Okay. So this is what we will have as a representation of this part in terms of this and this and this. Both these things are knowns from the previous step. This is the unknown, okay, and we want to solve for this. Okay. So next we are going to use this expression where in our equations here and equations here. So what do you see? That C into t dot at station I minus 1 is equal to f at I minus 1 minus k into t at I minus 1. So we can write like this. Here this is equal to, essentially I can replace this in terms of what we have already written. So what I will get is, I will get an equation in terms of t at the station I. Okay. So in the following we are going to arrive at that expression. Okay. So this now, from the first of the equations that we had written, will be equal to f at station I minus 1 minus k into t at station I minus 1. Okay. So this substitution I will do. Now from the next equation, if I multiply both sides with alpha delta t into alpha delta t, okay, so what I will get as C t dot at station alpha delta t C t dot is equal to this quantity, this minus this. Okay. So I can do the following, that this will be equal to alpha delta t f at station I minus alpha delta t k into t at station I. Okay, fine. So now what we will have implies we will collect all the terms corresponding to Ti on one side. Okay. So we will have C plus alpha delta T K into operating on Ti, okay, is equal to alpha delta T Fi, okay, plus 1 minus alpha delta T Fi minus 1, okay, minus 1 minus alpha delta T K into T I minus 1. Okay. So this is essentially the system of equations that we have set up, and you see that this is all in terms of the unknown Ti. Okay. This I will call as K bar at station I. So this will become K bar at station I into operating on the T, unknown T at station I, in terms of the F at station I plus minus terms which are obtained from the previous stations. So this whole thing will become as F bar at station I. Okay. So we will write K hat K bar at station I into T at station I is equal to F bar at station I. So this is the system of equations we have to solve, and then T at station I is equal to K bar at station I inverse into F bar I. Okay. So this is how we are going to solve the problem. Okay. Now we didn't say anything about the choices of alpha that we can take. Okay. Depending on the various choices of alpha, here we get different types of schemes. Okay. For example, if I go to our definition of this alpha family, okay, we generally what we are going to take is alpha is between 0 and 1. If alpha is equal to 0, you see we get a very interesting thing. If alpha is equal to 0, then we will get Tj at I minus Tj at I minus 1 is equal to T dot at I minus 1. Okay. So alpha equal to 0 gives me, so choice, if I put alpha equal to 0, T, the vector T at I minus vector T at station I minus 1 is equal to the vector T dot at station I minus 1, at station I minus 1. This approach is called the forward difference scheme. Okay, which means that in taking the time derivative at a current instant, I use the value ahead of the current instant to get the derivative. Okay. So value, the difference will be into delta t. Okay. So if I take the value ahead of the current station minus the value at the current station divided by delta t, that becomes my approximation of the derivative at the current station. Okay. This is the forward difference scheme. This scheme has its disadvantages. What happens is, if my time step, this delta t that we have chosen, is bigger than a critical time step size for the representation that we have taken, the discrete representation, that is for the choice of the degrees of freedom n or the choice of the mesh. If this is bigger than a critical time step size, then my temporal solution, when I do the time marching, the solution will diverge, it will blow away. That is, the solution in this case is said to be conditionally stable. That is, the stability or the propagation of the error in time, okay, is dependent in this case on what is the size of the time step we take. Okay. If now I choose alpha is equal to 1, if I choose alpha is equal to 1, then it's quite easy to show that then Tj at I minus Tj at I minus 1 is equal to delta T T dot J at I. That is, the temporal derivative at the current station is given in terms of the value at the current station and the value at the previous station. This is called the backward difference scheme. That is, the derivative is obtained by taking the value behind the current temporal station. I could take various other values of alpha. Okay, if I take alpha equal to half or 2/3, then we get the Crank-Nicholson scheme and the Galerkin scheme. Okay, so different choices of the alpha will give us different solutions. Okay, and different characteristics of the temporal solution. Okay, so we will look at the choice alpha is equal to 0. This will be forward difference. Alpha is equal to 1. This is backward difference scheme. Alpha is equal to half is the Crank-Nicholson scheme. Okay, this one is said to be conditionally stable. Okay, and these two are both stable schemes. Okay, now whenever we are choosing this time stepping delta t, we are doing an approximation in time. Instead of solving the differential equation for all times, we are solving it at discrete time stations. Then obviously that brings in errors. Okay, errors due to the representation of the function as a in time. So these are truncation errors that we are going to get. Okay, now there are also, because of the machine precision involved, that is, we are using single precision arithmetic or double precision arithmetic. Okay, especially when you are using MATLAB or Mathematica, unless you specify the precision, it will work with single precision. Okay, in that case, we are introducing further round off errors. That is, a number which should have been 2 is seen by the machine as 1.999. Okay, these introduce round off errors. They also can propagate in time. Okay, so when the round off errors and the truncation errors are always bounded, that is, they do not grow with time, the method is said to be stable. Okay, for if it is for all sizes of delta t. Okay, it does not mean, if the method is stable, that the solution is accurate. That is, depending on the delta t, my error can be large, but it will not grow in time. That's all it says. Okay, accuracy depends on how fast my solution converges to the exact solution for all times as my delta t becomes small. Okay, we have another definition here, which is called consistency. Consistency means that as delta t comes down, the approximate solution reaches or converges to the value of the exact solution for the system at that time, at any time t. Okay, so these are certain new definitions which have been inherited from the finite difference terminologies that are sitting there, but we will discuss those in detail later. Okay, so if I now take the forward difference scheme, the advantage with the forward difference scheme is that in the scheme of things that we have obtained, okay, if I go back to our representation here, what will happen is, if I, where is my equation? Okay, here, this part will get knocked off. So I'll get C into Ti is equal to, this will not get knocked off, delta T f at I minus 1, okay, delta T k into Ti minus 1. This is a matrix vector multiplication. Okay, so all we need to obtain is k into Ti. We do not have to invert k. While in many cases C can be reduced, this matrix C, because this will get knocked off, can be reduced to a diagonal form. Okay, we can do lumping of the elements. Okay, this you can see in a book on vibrations. There's a lot of literature available on this. So we can reduce it to a diagonal form, and in many times it will come out the way you choose the basis function and so on. It could come out to be diagonal. In that case, if this matrix C is diagonal, then you can obtain the values of Ti or Tj's at the station I explicitly, because you do not have to do a sophisticated inversion of C, because the inversion of C will give you 1 over the diagonal terms in the diagonal. Okay, so that leads to an explicit solution at the time station I without having to invert any matrices. Okay, so this is something which is very attractive about these schemes, because when I want to solve a problem, the behavior of a system in time, I have to solve for many time steps. Okay, and if I have a tool with which at a time step I can very quickly get the values of these coefficients without having to invert these matrices. Inversion takes a lot of time, n cubed operations in the case of a standard Gaussian inversion, okay, Gauss-Seidel or Gauss-Jordan inversion. Okay, then in that case, if this can be avoided, then we get a very quick solution and we can do a very efficient job of marching in time. So this is what the forward difference scheme is called an explicit method. With the understanding, it really is explicit when I do not need to invert the matrix C. If again my alpha is equal to 1, if I go to the backward difference scheme, okay, if alpha is equal to 1, then you see that here k is also sitting. K in general will not be diagonal. Okay, so it will make this whole matrix K bar as non-diagonal. Then we have to do the inversion. Okay, when you have to do this inversion, then the backward difference or any other scheme where these matrices have to be inverted are said to be implicit schemes. Okay, so if I go back to our two element problem that we had posed right in the beginning here, where we had this kind of a representation, and we had said our TFE in this case will be equal to sigma j is equal to 2 to 3 Tj as a function of time phi j, okay, plus T1 as a function of time phi 1. Okay, I have deliberately put this out because this will be enforced through the boundary condition. Okay, then I can put this in the formulation that we have taken, that is here n will become, we could take n equal to 3. Okay, in the various things that we have done here, n equal to 3 we can put, and we can go through the steps everywhere, n equal to 3, get to this matrix which will be a 3 by 3 matrix. Okay, now the bottom line will be that when we do all this business of inversion and this manipulation, then we have to apply the boundary condition. That is, again we have to force the T1I to be equal to the known value at that station, which again comes through the k hat matrix. That in the k hat matrix, I am now going to force the first diagonal term to be 1, all other terms in the first row to be equal to 0, all terms in the then I will modify the load vector in such a way that the first load vector entry becomes equal to Ti T1 at time t, okay, at time Ti, and all other load vector entries are suitably modified. So if I had to do it here, I will put F1 at station I will be equal to T1 at the time Ti, okay, and Fj for all j's at time station I will be equal to Fj at time station I minus k bar 1j, okay, into T1 at time station Ti. This I will do, and then I will set, after this, set k 1j bar equal to 0, k j1 bar equal to 0, and k 11 bar is equal to 1. Okay. So I will do the same things that we have been doing till now for the static problem in order to enforce the boundary condition that the temperature at time t equal to 0 is given. Now we didn't say how we are going to start. Till now we have talked about getting the solution at station I when the solution at I minus 1 is known. So we have to obtain the solution at time station 0, which is the initial conditions. So the initial conditions have to be specified. Okay, that is, this will mean T0 is known. Okay, this implies T at all points at time t equal to 0 is equal to some function t bar of x. How will I obtain this? If you remember, my TFE at time station 0 is equal to sigma Ti 0 into phi I of x is equal to I is equal to 1 to n. This is equal to what? What we will do is, we will say that at the nodes TFE 0 is equal to T bar at the nodes xi. Okay, this is nothing but Ti 0. So the nodal values of this given function at the nodes is taken to be the value of these coefficients, because that's what this function will be at the nodes. Okay, so initial condition gives me the values of these nodal temperatures at time t equal to 0. From there I start marching in time. So I construct all these solutions, especially in the Lagrangian setting. I can have these nodes. Okay, simply go read off the value of this function at this node. Okay, read off the value here, read off the value here. That becomes the value of this coefficient. Put it in, I get my initial temperature profile, and from there I start marching in time. Okay. In the next class, we are going to look at what do we mean by stability, accuracy, convergence, consistency, and all these issues, and then we'll go to the hyperbolic systems.